Welcome to this presentation in the series Electronics, the Story of One Human Lifetime by David Beams and Gary James. I am David Beams, Associate Professor Emeritus of Electrical Engineering, and I will be your host and genial raconteur for this presentation entitled Bonus Circuits Part 3, Applying the Beams Op-Amp Analysis Technique to Frequency-Selective Op-Amp Circuits with two capacitors. Just a recap of the Beams Op-Amp Analysis Technique, which I call BOAAT for short. It's a simple method for analyzing all manner of op-amp circuits consisting of an op-amp, an input voltage source, and two linear networks, network A and B. This is a common topology in many applications. Network A produces a voltage at the non-inverting input, which I call V sub P, which is a linear combination of the input voltage and the output voltage with weights A1 and A2. And network B produces a voltage at the inverting input, which I've labeled V sub N, which is a linear combination of Vn and Vo with weights B1 and B2. Then if we apply the virtual ground criterion, the op-amp will find an output voltage that drives Vp and Vn to the difference to zero, meaning Vp equals V sub N. And we combine the virtual ground criterion with the definitions of V sub P and V sub N and produce an expression for the transfer relationship V out to Vn in terms of these coefficients A1 minus B1 divided by B2 minus A2. It has an amazing range of applications, and we've already seen in the two preceding videos, the BOAAT method applied to circuits using resistive networks and circuits using networks in which there was a capacitor. Now, here we're going to be applying it to the networks involving two capacitors, like this Sallen-Key active low-pass filter. Now, before I move on to the next slide, I want to point out that the B coefficients can be read directly off the schematic. B1 is 0 because there is no connection from V in to this network. And B2 can also be read from the schematic because with an output voltage here, what fraction of it reaches V sub N? It's just a voltage divider composed of these two resistors. And just as a mention, with the value of R sub F that I have in this simulation, B2 is 1, and this amplifier is connected as a voltage follower. Okay. The network for determining A1, we apply an input voltage. We force the output voltage to be 0 and determine V sub P. And with some tedious, somewhat tedious network analysis, we get this as the coefficient of A1. The network for determining A2, we set V into 0. We force a voltage at VO and look at V sub P, and we get this expression. And then when we apply the coefficients to the BOAAT formula, A1 minus B1 over B2 minus A2, we get this expression. Now, just as before we proceed to do a simulation of this network, I want to point out that if the voltage gain of the operational amplifier is 1, if it's configured as a voltage follower, B2 is 1, which means RF is 0. And if the two resistors have equal values, which I've chosen, and if C1 is twice C2, which is almost the case here, I have chosen standard values for these capacitors that are almost in a 2-to-1 ratio. Couldn't hit it exactly. Anyway, if equal resistors, 2-to-1 capacitor ratio, unity gain, that produces a so-called Butterworth or maximally flat frequency response. And as you can see, this circuit is very close to it. Here is the magnitude response, 0 decibels or unity gain at low frequencies, passes through -3 decibels at 1 kilohertz, and then rolls off at 40 decibels per decade. Here is the phase response. Okay, so now let's take a look at another two capacitor circuit. This is a two-pole all-pass network. Okay, and before we move on to the next slide, I'll point out that you can read the B1 and B2 coefficients directly from the schematic. Notice that these two resistors in this voltage divider have equal values, which will give me that B1 and B2 are both 1/2. And this, by the way, is bonus circuit number 9 available for your download. Okay. Here's the network for computing or determining determining A1. We apply an input voltage, force the output voltage to 0, and find V sub P. And this is the expression for it. Now, I've made the assumption that the two capacitors have equal values, which is you'll simply see, and I'm using the notation R23 to represent the value of R2 in parallel with R3. Here's the network for determining coefficient A2. We set V in to 0 and apply a voltage at the output and determine V sub P. And this is the expression for A2. And now, again, letting Ri equal RF in the schematic, which makes B1 and B2 1/2. Now let's apply the BOAAT equation. And this is the transfer function we get. Now, I've done a little additional work on this so that the coefficients of S squared in both numerator and denominator were unity, because it helps clarify a point that I want to make. If resistor R1 is twice R2, then this term is 0. And this term is 0. And then the coefficient of the linear term in S, in the numerator and in the denominator, well, in the numerator, it's -1 over CR3. In the denominator, it's 1 over CR3. If the resistor ratio is 2:1 and the two capacitors are the same, then the circuit shows an all-pass response. And here is a simulation of that circuit. Here is the magnitude response. Here is the phase response. Phase response starts at low frequencies, approaches 0 degrees, and asymptotically approaches -360 degrees at high frequency. Unity gain across all frequencies, continually varying phase, just what we'd expect from an all-pass response. Now, just to make sure that my calculations were right, I took the transfer function derived with the BOAAT method and used it to compute the frequency response of this network using Octave, which is an open source analog to MATLAB. And this is a plot of the frequency response of that network. Here's the magnitude response, which is flat at 0 dB. And there's the phase response. And I compared them to the LT-SPICE simulations, and they matched. So I'm confident that my derivation of the transfer function was correct. Why would you use such a thing? Well, let me show you an example of an actual application of that very topology. This was part of a system in which I needed to generate quadrature sinusoidal signals. By that I mean two signals 90 degrees out of phase, like cosine and sine, over a fairly wide range of frequencies. And I found this method, this circuit shown here, in an article in a magazine called RF Design from, I believe it was March of 1989, entitled Design of Constant Phase Difference Networks. You take one sinusoidal input source and you produce two sinusoidal outputs, and the two outputs remain 90 degrees apart in phase over a fairly wide range of frequencies. In this case, with this design, the frequency range was from 215 hertz to 4.75 kilohertz. And this system consists of two parallel branches. In each branch consists of two cascaded two-pole all-pass filters. And with the values shown here, by the way, this is bonus circuit number 10 available for your download. This is the frequency response. Magnitude response of both networks is 0 decibels, flat. But now notice that the phase response of the two networks, the difference between the two phase responses from a little over 200 hertz to somewhere past 4 kilohertz, that difference in phase is 90 degrees. VO3 leads VO1 by 90 degrees. So I could call VO3 the cosine output, and VO1 the sine output. And just to reinforce what this means in maybe a more concrete way, I did a transient analysis with that network using a 1 kilohertz sinusoidal source. And here's a plot of output voltage 3, that was from the lower branch of the network, and output voltage 1, which is this yellow trace, that was the upper branch of the network. And you can see that the output voltage 3 is leading output voltage 1 by 90 degrees. Signal zoom quadrature. All right, let's put the wraps on everything for today. Remember, the link for all of these resources is in the video description. And if you find this stuff useful, then please, money would be good, but probably, yeah, I'm not really expecting it. I mean, you could surprise me, but we'll settle for nice comments. And just like to know that this has been useful to you. Anyway, as always, we appreciate your visiting with us. Keep those cards and letters coming. I am David Beams, and it's been my privilege to be with you today, and I hope to see you again soon in another video from Electronics, the story of one human lifetime.